So today we will start a series of several speakers, of more junior speakers who will be applying for postdoc positions soon and who will be telling us about interesting physics they are doing. And the first two talks will be by Zachary Picker and Ludovic Sipos. And they will be talking about different topics. So the first speaker will be Zachary Picker from the University of Sydney, and he will be talking about probing the universe at the intersection of gravity and particle physics. So Zach is a PhD student with Archel Kovakidze and is, as the title says, working on connections between particle physics and gravity and physics at the intersection of that. So please, Zach.
Cool, thanks. Is the bottom of my slide still cut off?
It looks like it. That's better.
Okay, yeah, I don't know, the toolbar keeps popping up. Anyway, thanks for having me. So I gave a more technical talk a few months ago for a CPPC seminar. So I thought this time I'd do something a little bit more broad about the research I've worked on throughout my PhD, and maybe a little bit philosophical in some sense. One exciting thing I learned, though, is that there's an endless source of free content for presentations. If you just take the name of your slides and you put it into an AI art generator, and then you can get these sort of pretty images, which don't really say anything, but it looks like they might. So maybe one day we can make all of our plots like that, but I'll get started. So I'm going to talk about gravity and particle physics and phenomenology related to them. So as we all know, the standard model is perhaps the most successful theory, maybe ever, you could say, at least perhaps the most precise in predictive power. But when we add gravity to it, all sorts of problems come up, very exciting problems, fun ones, including, for example, the cosmological constant problem, which you might call the least successful prediction in all of science, perhaps ever. Which is off by 120 orders of magnitude, which is pretty dire. And so all these things are really fun problems at the frontier of fundamental physics and physics in general. But part of the problem is that if you want to be working on those things and making progress, there's a lot to know. There's a lot of things to learn, and you can only know so many of them at one time. So I've drawn this sort of illustration showing the different things you can get good at between particle theory and gravity and astronomy. And if you really want to work in the intersection of gravity and particle physics, you have to live in this fidget spinner sweet spot, as I've called it. And well, seeing as this is in some sense an advertisement for me, I could put myself in the center of this spinner. But that probably wouldn't be accurate. Maybe when I look like this, I will truly be in the center of these. But that's the goal at any rate. But regardless, I think that this lens of looking for the phenomenology in between gravity and particle physics is a sort of useful way to think, maybe not just about the work that I do, although I've certainly put the things I'm most interested in at the center of this bridge. But in general, about the phenomenology of the universe that we're looking to probe in the next, I don't know, few decades. So as far as I see it, there's three ways or three questions you can ask to find new physics out of this diagram. The first one is, you might ask, well, what happens when we modify gravity? So if you leave general relativity and you choose some other theory, how does that trickle down phenomenologically into all these other aspects? The second question is, what happens if we leave gravity the same, but we find new solutions within it? And of course, that's going to affect your solutions more in the middle. It's more a direct impact on those concepts. And then the third question, of course, would then be, what happens when we take our regular particle physics, which we like to do in flat Minkowski background, and we put gravity into the mix also? So that's going to affect your particle physics calculations, but that will then leak into the universe phenomenology just the same. And so I thought it would be an interesting idea to sort of frame the research I've done in terms of these three questions. And it started off, I suppose, at the beginning of my PhD, we were asking the question, okay, what happens when we change gravity? What when we use a different gravity theory? So one thing you can do is, well, if you change your gravity theory, then you can compare that to observation and constrain that new theory. So one thing we were looking at was this theory called quadratic gravity, which you might say is perhaps the most generic way to extend general relativity. It's sort of relatively straightforward. It adds extra gravitons more or less. And what happens here, we found, was that black hole binaries deplete energy more quickly. And you can compare that to the gravitational wave signature from LIGO and constrain quadratic gravity. You can constrain the masses of these extra gravitons, noting that when the masses go to infinity, you recover regular general relativity. So that's the meaning of this constraint here. And then you can also do the opposite of that idea, which is you can take a new theory and you can use that to re-examine the sort of observational landscape of the universe. And in this context, we wanted to look at microlensing, which is a phenomenon where a compact object, so maybe a black hole, passes in front of a distant light source, and the light rays get bent around it and so magnified. And you can use this to place relatively tight constraints on the amount of, say, black holes as dark matter in a particular mass range. And so if you change gravity, you would think that perhaps the microlensing signatures would get changed also. So this is something we were exploring for a while, but we found, well, we looked at two theories. One was the quadratic gravity that we were studying before, and we found that we had constrained it too tightly in order to make any observational signatures that we could tell. And then we looked at this other theory called bimetric gravity, which is it's pretty much you have an extra massive graviton, but it's coupled in a specific way. It's essentially a generalization of the old Fiers-Pauli massive gravity from back right at the beginning of general relativity. And this has an interesting mechanism which actually screens it at close range. You can get, it's called the Weinstein mechanism. And that allows you to get around some of the solar system constraints. But it turns out, well, because of that factor, essentially, you need the impact parameter here to be much larger than it is for all of the microlensing experiments that we're able to do right now. And so you either need the source to be farther away, so pretty much farther away than Andromeda, because that's the, I guess, most distant one we can use for these observations, or you need much more massive lenses, and neither of which are compatible. So we got sort of a null result on that one, but I can draw both these ideas on my illustration. So that first paper is more up here, and this null result is down here somewhere. Okay, but let's look at the second question. What happens when we find new solutions within general relativity? And well, this is one that many of you have probably heard me talk about at length, and I also sort of gave a longer seminar on this. But the idea that we wanted to investigate was primordial black holes, which are black holes in the very early universe, can't be described by Schwarzschild metric, so the usual black hole metric. And that's because at long distances, it needs to look like the FLRW, cosmological metric. And also, of course, the black hole will be surrounded by a hot, dense fluid, which is just not true in the Schwarzschild case. So you need to find a new kind of black hole solution. And this was actually something that was noticed right at the beginning of primordial black hole study, where Zildovich and Novikov both found together that primordial black holes have this runaway accretion problem, which makes them not viable as a theory. But Carr and Hawking responded that actually, if you properly take the long distance limit to be an FLRW metric instead of just flat space, then you get around this issue. And that began the study of primordial black holes as a field, interestingly enough. So we studied a particular solution known as the Thakurta metric, which I won't get into too many details, but you can find my ramblings on that in other places. It's essentially a black hole solution that grows as the universe grows, so proportional to the scale factor. And what that means is that in the early universe, it's a lot lighter, or it's effectively lighter. And the question that we're interested here is whether these black holes described with this new solution could be dark matter or not. And there's a lot of interest in LIGO-sized primordial black holes being dark matter because, well, I guess they're all the rage these days, seeing as LIGO is up and running. And if you look closely at the LIGO mass range, we're actually quite close with all these constraints. If you just give them a little bit of uncertainty budgets there, you can get almost all the way up to 1 for the fraction of dark matter in black holes, except for the fact down here that in the early universe, primordial black holes will form binaries very efficiently. And so LIGO would be able to see them coalescing, and you can place strong constraints from not seeing that. However, with the Thakurta black holes, because they're so much lighter in the early universe, they struggle to decouple and form binaries, and so you can totally evade those constraints. So that was one thing we found. And then the second question to ask about these new solutions, this Thakurta solution, is what happens in this asteroid mass range, which is totally unconstrained. Here, the lower edge is from black hole evaporation, where if they evaporate with a lifetime shorter than the age of the universe, well, they're not a good dark matter candidate because they're not around anymore. And we found that because the Thakurta black holes are so much smaller in the early universe, and the temperature of black holes is proportional to the surface gravity, so 1 on the mass, you'll find that it's actually a much larger black hole which evaporates before today. So you can pull this bound here all the way up here, almost entirely closing the asteroid mass range. So that was a second paper we put out, and I can plot these on our favorite picture more in the top area, which sort of goes between the two, maybe sort of like how we would expect. And finally, the third question is, what happens when we add gravity to known particle physics processes? And this is something we were investigating in the context of the axion and the strong CP problem. So the usual way this problem is phrased, let's see if I can do this in 30 seconds, is that the strong force has all these different discrete vacuum configurations, and you can tunnel between them with these things called instantons. And these instantons force you to add an extra term to the standard model Lagrangian, which goes like this theta term, which you might very heuristically think as something like the size of these potential wells. And then with the gluon field strength tensors. And this theta term violates CP conservation in the strong force, which isn't observed. So we have to introduce a scalar particle called the axion, which exactly cancels out this. It's a very neat theory, but unfortunately, when you include gravity in the picture, you find that there's actually more kinds of vacuum configurations you can move between, and a different kind of instanton, which does that, called colored Iguchi-Hansen instantons. And for sort of technical reasons, they sort of wind up your vacuum 3 instead of 1 compared to the BPSD instantons. And what this does is it adds a second theta angle to your standard model, and which also violates CP, but now the single axion is only able to cancel one of these two values. You can't cancel both of them. So the solution that we proposed was to, well, add a second axion, which has to be coupled to the first one, which we call the companion axion model. And we wanted to study the phenomenology of this sort of model. So I've illustrated that sort of here, where the regular axion is in red, and the second companion axion, which needs to be added, is this lighter line here. And these dashed lines indicate the coupling between these two. So in order to solve the strong CP problem, you end up like, for any of the first axion, you fix the second axion down here. And interestingly, if one of them is constrained, they're both therefore constrained, as long as you'd like to solve the strong CP problem still. So compared to the regular axion case, there's two free parameters now, and that's the vacuum scales of these two Pechiquin symmetries, which we've gone with F and F dash essentially. So instead of being a band where the one axion lives, now we have an area in order to constrain. And so I've plotted that here. One of the vacuum scales is here, and the ratio of the other vacuum scales is on the y-axis. And what we want to do is constrain this model by looking at how both these axions couple to the photon. And so there's a number of ways this is done. These are all sort of the same things you do with the single axion, but recast into our model. So if axions are produced inside of stars, they might cool them down too quickly. And in our case, that'll happen even more so because there's two axions. So these constraints are a little bit tighter. Then you can ask, well, if these axions are the dark matter in a halo of the Milky Way, then can we detect them using some kind of resonant cavity or like radio antenna resonance? And well, I'll talk a bit more about whether these axions can be dark matter in a second, but you can see these constraints and these diagonal bands here. Another thing you can do is try and detect axions from the sun, and you can build like a big magnetic chamber and convert them back into photons and detect them that way. And in our case, the constraints are a little bit weaker than they usually would be because the two axions can oscillate between an electromagnetically hidden and active state. So so less of them will reach the detector than usual. And finally, light bosonic fields can spin down black holes. And the fact that we observe black holes with spin places some constraints on these kind of models. Although I have to say that these constraints are a little bit contentious. Different groups have sort of roughly different areas where these apply. And well, as I was saying, looking at these axions as dark matter is a slightly more complicated problem. I mean, it's already complicated in the single axion case because you have sort of misalignment mechanism production of axions as well as topological defects, which can produce axions too. In our case, the misalignment mechanism is more complicated because you have two coupled equations. And it also will depend on whether these the vacuum scales happen before inflation or after inflation, or a mix, one before and one after inflation. So in the case where they're both broken before inflation, this sort of rainbow colored band shows you where the sort of preferred dark matter location is for these axions, for them to constitute all the dark matter. It could be in these other areas, but that would imply a sort of fine tuning, which almost destroys the point of the axion as a solution in the first place. And in the case where one is post-inflation and one is before inflation, then you live in this band here. And finally, if they're both after inflation, then the axions have to be exactly on this line to constitute the correct dark matter abundance. One interesting thing to note is that in our case, we actually don't have a domain wall problem, where for the single axion, you might have these when you break the Petroglyph symmetry, you have this residual symmetry, and you can get these topological effects called domain walls, and they might dominate the energy density of the universe, and that's known as the domain wall problem. In our case, though, because we have two symmetries, and both of them are broken to different kinds of discrete symmetries that aren't compatible with each other, that puts a pressure on the domain walls and causes them to annihilate extremely early on. So you actually solve the domain wall problem automatically, and at the same time produce a lot of gravitational waves. And we calculated the signature of that, and the observable signature by SKA would be in this purple band here from gravitational waves of domain wall collapse. All right, so well, that second paper is coming. I think we're going to put it on arXiv probably after this talk. So take a look out tomorrow. Hopefully you'll see it. And the first paper on the photon couplings we put out a few weeks ago. So that lives somewhere in this middle band, more or less. All right. So what are the morals and takeaways here? I sort of think this drawing is a nice way just to I don't know, get a qualitative idea of where is the frontier of physics, and what happens when you tweak one of these theories a little bit. So if you change gravity, you can see that this sort of will trickle down into all these phenomenological things that we can probe the universe with. And you can either use that to learn about the universe, or you can take your observations of the universe and use that to learn about fundamental physics. So you have a sort of exciting interplay between those two things. And we know so little about a lot of these things that all these unanswered questions, well, when you play with them, you get surprising phenomenology. And in my opinion, that's, well, it's a fun way to do physics, and it's a fruitful way. There's an endless supply of ideas, and so there'll be an endless supply of interesting things to see. And that's really all I wanted to say. Yeah, I actually kept that pretty short, so thank you.
So thank you very much, Zach. We have time for questions. Who wants to go first? Maybe I start. So can you go back to slide 27? So yeah, right. So you get those. You have those two strong CP problems, in a sense, and so the usual constraint, right, comes from neutron electric dipole moments, and that constrains the theta QCP to be less than 10 to the minus 10-ish. So that theta CEH, how small does it have to be, and what constrains it? Also the neutron electric dipole moment, or something else?
How small does it have to be to, sorry, say it again? Yeah,
so you said basically you want to solve those both strong CP problems, technically, those both problems. You want to make both of those theta parameters small. How much is that theta CEH constraint, or how small does it have to be?
It's not going to be, I believe, it probably only a couple of orders of magnitude larger allowed than theta QCD. Well, maybe it'll be more clear if I show the axion potential that you get as a result. So this is, you get two cosines instead of the usual one, and there's two axions in each. And the second cosine has this extra parameter, which makes it smaller by about 1 to 2 orders of magnitude. And so I suspect this is the same kind of order that you would need to twiddle with the neutron dipole moment.
Yeah, I'm not an expert how it enters into the calculation exactly.
Oh, I'm also really not an expert on the neutron dipole moment. Yeah.
Yeah. Thanks. Any other questions or comments?
Yeah, maybe I can ask a very broad question. I think is the only link that you didn't explore constraining like gravity with particle physics, like modified gravity with particle physics. Was that one of the links you drew? Oh yeah, you have dark energy that written there. Do you have any ideas for how you might extend your work to this one as well and cover all bases?
Oh, for this one down here.
Yeah.
Yeah, well, maybe I have ideas and I shouldn't say them. But
Fair enough.
Yeah. I don't have anything particular on my mind at the moment, but dark energy. But it's exciting.
That's good. Well, one more question to those. Can you go back to those plots when you constrained that space of the companion axion? I just wanted to see once more how. So in those bands, okay, you constrain those scales FA and FA, right?
Yeah. So this scale here essentially corresponds to the mass of the first axion, and because of the way they're coupled, the diagonal lines are lines of equal mass for the second axion, essentially.
Okay. So that's an equal. So those axions that the mass scale roughly. So wait, I think you had it on the next plot. There was the range for the masses. That was. So you have more like heavier.
So the first axion is more or less the same as the usual axion case in mass, and the second one can be significantly lighter.
Because it's related
roughly the same.
Yeah. Okay. No, thanks. Any last questions? But if not, then I think we should thank Zach again for a very nice talk and good overview over his PhD.